So here we are at the end of week 7. We've got Thursday and Friday to go of this week. And then we will be getting into week 8, the very last week of class. So if we scroll all the way down over here, during week 8, when we meet on that Tuesday, it's essentially going to be a big review day. So we'll be going over kind of everything that we've talked about so far this term in a very condensed fashion, hitting on some of those major points to hopefully help kind of jog your memory for the final exam. The final works very similar to how the midterm worked. So you can see that it is scheduled for May 24th, which is the Monday of next week. And it is due by May 26th. So for everybody besides Namarik, and Namarik, I'll make sure to send you a copy of the exam a little bit early so you can work on it early since I know you're traveling that week.
Okay, thank you.
But for everybody else, the exam will go live on Monday, May 24th, and then you'll have all day on Monday, Tuesday, and Wednesday to work with it. So it's due by the end of the day on Wednesday, the 26th. Again, it is very important that you get your final exam turned in by the end of the day on Wednesday, because final grades are due on Thursday at noon. So I only have a couple hours after the final exam closes to get all of the finals for all of my classes graded and then turned in for a final grade. So if you turn your exam in late, there's a good chance that I won't be able to grade it and you will end up getting a 0 on it, which would be a very, very, very bad thing to happen for your grade. So just like the midterm, it's available in a Google Doc version that you can fill out just as if you're doing it like pen and paper style, and a Google form version that is split up into sections covering different things that we've talked about over these last couple weeks.
Are we allowed to use notes?
So the Google Classroom will be available to you while you are taking the exam. So you will have access to all of your own notes that you've taken and also all of the notes that have been posted on here over the last 8 weeks or so. The exam also, about half of the exam, maybe like 50 to 60% of the questions are stuff from the most recent couple weeks. So I think we took the midterm in week 4, which is when we were talking about elements and compounds and ionic bonds and that good stuff. So about half of the exam will be on chemical reactions. The good news is that there are not going to be any balancing equations questions on the exam. So if you're confused by that when we went over in class with the coefficients and changing them from a 0 to a 1 to a 2 and stuff like that, none of those are going to be on the exam. So don't worry about that. But there could be some questions about those chemical reactions, the exo versus endothermic, creating or not creating new atoms. Some questions about SI units and density, so the meters, grams, and liters, converting between them, and density and what it is, how you calculate it. And some questions about the laws of motion. And so 50 to 60% of the exam will be the new stuff, but then 50 to 60%, or 40 to 50%, excuse me, will be from the entire term. So it could go back to talking about properties of matter and solids, liquids, gases. It could go back to talking about neutrons, protons, the periodic table, atoms, and electron shells, and questions about mixtures and compounds and bonds and stuff like that. So everything that we have talked about so far in this term could be covered on the final exam. So again, that exam will go live on Monday. On Tuesday, we'll spend our class time reviewing material that's covered on the exam, kind of catching back up on stuff that we may have talked about long ago. And then Wednesday is your final day to work on the exam and the your last chance to get it turned in before the end of the term. I think that's the main thing that I wanted to say about the final. The other important thing about Wednesday, like I was talking about on Tuesday, is that besides the final exam, all past homeworks, assignments, questions in the Google Classroom, if you've not turned them in yet, they are all due by the end of the day on Wednesday. So if you're currently missing something in the Google Classroom, that means that it has a 0 in the grade book. And if you want to get a grade for it, if you want me to look at it and give you a grade, you have to complete it by the end of the day on Wednesday. Any work that is turned in late won't get graded and won't count towards your final grade. So besides making sure to turn in the final on Wednesday, you also want to be sure that you've gotten any of your past homework and assignments turned in as well. If you're not sure if you're missing any assignments or you want to double check and see if there's anything that you still need to do, you can always reach out to me and send me a text or send me an email and ask about any missing assignments. And I can go through and pretty quickly find if there's anything that you still need to turn in. Unfortunately, I have too many students where I can't go through and send out emails to every single person individually saying if there's anything you need to turn in. But if you ask me about it, if you send me a message, either a text or an email, I'm more than happy to help you out and look for those assignments for you. Kind of let you know what you still have to work on. Any questions about the final exam so far, or missing assignments, or anything related to kind of the end of the year and wrapping up the school year? All right, cool. So like I said, today we're going to be talking once again about those laws of motion. On Tuesday, we talked about the first two laws. Let me find a good slide for them. Here we go. So on Tuesday, we talked about the first two laws. The first law saying that an object at rest or in motion will stay at rest or in motion unless acted upon by some outside force. And the second law, which was that equation of force equals mass times acceleration. So if you know the mass of something and you can observe the acceleration, you can use that to calculate how much force was put on that object. So today we're going to wrap up talking about the laws of motion by going over the third of our three laws of motion, which says that for every action, there is an equal and opposite reaction. And exactly what that means and how that works is what we are going to be talking about today. Alrighty. So our third law of motion, also sometimes called the law of action and reaction, says that when one object exerts a force, a push or a pull, on a second object, the second one exerts a force on the first that is equal in magnitude and opposite in direction. Whew. That is a whole mouthful of words right there. Magnitude, direction, forces being exerted. What is going on? What does this actually mean? Well, the best way to show you is go through a couple different examples with you. But the main idea is that if you push on something, that something will push back on you. For every action, there's an equal and opposite reaction. So every time one object exerts a force on another, that second object exerts an equal force back on the first one. If I take this empty water bottle and take my hand and exert a force on the water bottle exerts a force back onto my hand, right? My hand doesn't just go straight through the bottle, but it hits it, it makes contact, and then there's a force that is resisting my hand going any further. That is the basis of what the third law is talking about. A force being exerted in one direction will have an equal force exerted in the opposite direction. So an excellent example of the third law of motion is something like the space shuttle taking off, a rocket going up into the air, right? So the way that a rocket launch works is that all these big things that the shuttle is connected to are basically just fuel pumps. And there's all sorts of different types of fuels that are then burned, they're set on fire, which produces a whole bunch of hot gas. So all of this stuff shooting out the bottom of the rocket ship, that is all hot gas that is being forced out of the rocket boosters because of all this burning going on inside. So the gases get pushed out the bottom of the tube. So the gases are going down, right? All this fire and stuff is shooting down out the bottom of the rocket ship. When they do that, the rocket ship goes up, right? Gases go down, rocket goes up. That happens because of this third law of motion. There is a force that is pushing the gas down and out of the rocket ship, which means that since they are being pushed down, there is an equal force that is pushing the rocket ship out. So basically, as those gases shoot down out of the rocket, it causes the rocket itself to go up. All right, gases go out this way, rocket goes up this way. So here's kind of a zoomed in view of one of our rocket engines. And as there's exhaust that comes out of the engine, as all of those hot gases burn and shoot out the back of the engine, it causes the engine itself and the rocket ship that is attached to it to shoot forward, to go this way across space or this computer screen or whatever it is that might be. And that's because of the third law. For every action, there's an equal and opposite reaction. Because there's a lot of force pushing this way, coming out of the rocket as exhaust, that means that there's a lot of force that's going to be going this way to move the engine and move the rocket forward. You can also think about the third law. If you see a bird flying through the air, birds also rely on this third law of motion in order to fly. So the physical way that birds are able to fly is by flapping their wings right here, right? In order for a bird to lift off from the ground, it spreads its wings, starts flapping, and then up and away it goes. What is actually happening when it flaps its wings? Well, as the bird flaps its wing down, it pushes on the air that's below it, right? So if you've ever driven in a car and stuck your hand out the window, or you've ever, even if you just move your hands back and forth really fast, you can feel them pushing on the air that's around them. That's what birds are doing with their wings. They're taking the air that's around them and they're pushing it down. They're pushing it down. They're pushing it down. So as the birds push down on the air with their wings, the air pushes up on the bird. And this is what gives them lift. This is what gives them the ability to flap their wings and fly above the ground. They're generating lift, they're generating the ability to take off from the ground by pushing on the air. So you can even see it in the little video that we have here, the little GIF. You can see that when the wing goes down, the bird's body goes up. And then similarly, when the wing goes up, then we're not pushing on the air anymore. The gravity starts to take over and the bird starts to go down. But whenever it flaps its wings, the wings go down, but the body of the bird goes up off the ground. So as the bird pushes down on the air pushes back up on the bird, allowing it to fly. So it's called an action-reaction force, or in the earlier mouthful, when I said that a force has a second force that's equal in magnitude and opposite in direction. Magnitude is just a fancy way in science of saying like amount. So the size of the force on the air equals the size of the force on the bird. The same force that the bird uses to push down the air is going to exert that same amount of force, that same amount of push back up on the bird. So equal in magnitude. Air pushes down with a certain, or bird pushes down with a certain force. Air pushes up with a certain force. But opposite of direction. Bird pushes down, air pushes up. Rocket ship engine shoots out gas to the right. Rocket ship travels to the left. So they're always going to be exact opposite directions from each other, and they're going to be equal in force. All right. So we're going to talk about a whole bunch more examples of this third law of motion. But does anybody have any questions so far? Is there anything about this third law of motion that you're still really confused or really lost about?
No questions.
All right. Cool, cool, cool.
I'm good.
Awesome. Thanks, guys. All right. So imagine this. Oh, and I can actually do an example for you because I am sitting here in a wheelie chair. So imagine that you're standing on a skateboard, or you're like Mr. Stanley and you're sitting at your classroom desk in a chair that has wheels on it. And you're on a skateboard and you push against the wall, or you're on a rolly chair like me and you push against the table in front of you. So the force that I exert is going to be going towards the computer screen, towards you guys, right? I'm going to put my hands on the table and I'm going to push in this direction, right? But what happens when I do that? Well, let's see here. I'm going to take good grip on the table. Let me lift my legs off the ground and push. Whoa. I went backwards. I went this way. I pushed towards you guys, but I went backwards away from you. And that's because when I pushed on the table, the third law says that the table is going to push back on me. So even though my arms and my strength pushed towards you guys, towards the computer, the table pushed back on me. And the table, well, actually this table also has wheels, but they are locked in place, so they aren't going to move. But my chair and my wheels are very good at moving. I can slide it all around. So when I pushed on the table with a certain force, the table pushed back on me with that same amount of force. That force wasn't enough to get the table to move since the legs are locked in place, But it was enough to get me to move since I'm on a rolly chair. I could roll backwards. So that's what the third law is all about. If you're on a rolly chair or you're on roller skates or you're on a skateboard and you push against a solid stationary object like a wall or a table, that wall is going to push back on you with equal and opposite force. So opposite direction, equal amount of force. Same thing with if you're walking along in like your front yard or you're going on a hike and you go to step over a rock, but the edge of your big toe catches it. Bang. It hurts, right? You're like, ow, geez Louise, that sucks. I hate banging my toe against stuff. It's so unexpected and it feels like it hurts so much more than it should. Well, the reason why it hurts so much is that when your toe exerted a force on that rock, the rock exerted that same amount of force back on your toe. The harder you hit your toe against it, the more force the rock exerts back on your toe, right? If you're just kind of slowly walking along and you bump your toe, maybe it's going to hurt a little bit. But if you're winding up to kick a ball or something and you kick forward really hard, but you miss and you hit a rock or the wall or something like that, that's going to hurt a lot more because you are exerting a lot more force in the forward direction. So the rock or the wall exerts a lot more force back on your toe and makes it hurt. Opposite direction, equal amount of force. That's what we mean in the third law when we talk about these action-reaction interactions. So the action is you or some object doing that initial push or pull. The reaction is the wall or the rock or the air pushing back on that initial force. Very similar idea to a rocket ship you could see in your very own home with something like a balloon, right? If you ever held on to a balloon, you know that right after you blow it up, you have to close off that little neck right at the bottom, right? If you let it open a little bit, then it'll start making like a funny sound. But if you just completely let it go, what happens? The balloon, which was sitting in your hand, when you let go of that neck, all of a sudden it's going and starts flying all around the room. The reason it's doing that is because as air comes out the bottom of the balloon, there's air that is rushing downward. There's a force pushing the air down out of the balloon. So as that air is pushed out of the balloon, it then pushes back and the balloon is forced upward and it goes and zooms all around your living room. So as air goes down, balloon goes up. Very similar or the same basic concept for how a rocket ship works. As gas goes out, object goes up. Same thing with when you're nailing something in, right? Unless it's like a super thin wall or a super thin piece of plastic or something, it takes you a couple times to nail the nail into the wood. And that's because when the hammer is swinging forward and exerting a force on that nail, the nail and the wood that it's going into is exerting a force back on the hammer. And so you have to do multiple hammer hits in a row because you have to overcome that force of the wall and the nail. You have to push the nail deeper and deeper, even though it is pushing back on your hammer each time you hit it. So some other great examples of the third law. Let's say that you're going out on the lake and you're going on like a kayak or a canoe trip, right? So at the very end, you're coming back into shore and you're pretty close to the edge. There's still a little bit of water under you, but you're like, oh, I can probably get out now and it'll be fine. So you go to stand on the edge of the boat and step forward. Well, if your boat is just floating in the water, you probably are going to quickly be floating in the water as well. Because as you stepped forward to leave the boat and go onto the shore, your foot is pushing the boat backwards, right? You are trying to go this way, but that force is pushing the boat in the opposite direction. So the boat is going to shoot out from underneath your foot, and you're going to end up face first in the water. Your initial action step forward caused the reaction of the boat being pushed backward. Equal force in opposite direction.
Yeah, it's not fun.
Yeah, exactly. You always want to be careful whenever you're getting in and out of boats. You don't just want to step on the edge and then step forward and be like, oh, this should be fine. The same exact third law is the reason why we're able to swim through the water. Very similar to how birds fly through the air. So as you're swimming, you're putting your arm out into the water and then pulling it back. And then your other arm goes out and back, and then out through the air and back, and then out and then through the water, and then out and then back through the water, right? So you're swimming forward, you're constantly moving your arms behind you, right? You swing them up front and then you move it behind you. So when you do that, you push the water in front of you backwards, right? And what happens if you reach out and push the water in front of you backwards? You get pushed forwards. All right, so even though you're pushing the water backwards, you are going forwards. And it's all because of this third law of motion. So as your action pushes on the water pushes back on you. It pushes back on your hands and your feet as they kick. So you're pushing the water in the backwards direction. So the water pushes you in the forwards direction. And that's what allows you to swim across the top of the water. So if you do end up in the water because of the third law, taking that boat out from under your feet, you can swim to shore because the third law says that you can push on the water and the water will push back on you and send you forward. All right, same idea with when somebody hits a baseball with a baseball bat. All right, I don't know if you guys have ever hit a ball before, especially hit one that was traveling pretty quick, but you can feel it when you make good contact, right? It's not like you're just swinging through the air. You feel that force of the connection. And that's because the ball, it was going this way, and then it connects with the bat. And the ball exerts a large force on the bat. But the reason why the ball shoots off and maybe even scores you a home run is that the bat exerts that same force back onto the ball. So while the baseball is putting a force on the bat to the left, the bat forces the ball back to the right. The bat is a lot heavier than the ball, and it's sitting in somebody's hands who's holding it tight and not letting it go. So the bat's not really going to go anywhere. The ball is small and doesn't have anything stopping it from moving, so it's going to shoot back off in this direction. So the same force hit both objects, but the bat stays mostly still because it's in someone's hands. But the ball, that force will shoot it up and maybe even out of the park. So third law says that these two objects will exert forces on each other, and those forces will be equal amounts, but opposite in direction. Same thing with any two objects. Literally, even if you had like an apple and a cup on a table and they bumped into each other, they would exert a force on the other. As the apple pushes on the cup pushes back on the apple. So you have these pairs of forces that are equal and opposite. The force of something going one way will have a reaction force going the same amount in the other way. So if we go back to that very first time that we saw the third law of motion, it might make a little bit more sense now. When one object exerts a force on a second object, the second one exerts a force on the first that is equal in magnitude, so the same amount of force is all that means, and opposite in direction, going the other way. As gases shoot down and out of the rocket shoots up into space. As I push on the table in front of me, the table pushes back on me and sends me backwards. As birds fly through the air, their wings push down on the air, and so the air pushes back up on the birds. Two objects exerting forces on each other that are equal in magnitude, the same amount of force, and opposite in direction. They're directly opposed to each other, either up versus down, left versus right, in versus out. All right. Does anybody have any questions about our third Newton's law of motion? All right, so if we go back to that original slide that showed us the very first time that we saw all of these laws. There we go. So these three laws of motion are laws because they are true of everything in the universe. Everything that's able to move, everything that's able to exert a force on another object, whether you are a water molecule or a planet or a sun, no matter how big or small that you are, all of these laws of motion are true. So our first law describes how things change their motion, right? It says that if something is at rest, it'll stay at rest. And if it's in motion, it'll stay in motion at a constant velocity. So it'll keep the same direction and same speed unless acted upon by an unbalanced force. So we need some sort of new or greater force to come along and change our motion. If that doesn't happen, then we're going to stay still, or we're going to stay moving in the exact same way as we were before. So the first law basically says that we need force in order to cause motion. No force, our motion will stay the exact same. If we're sitting still, we're going to keep sitting still. If we're moving in a certain way, we're going to keep moving that exact same way. So again, on Earth, we talked about major unbalanced forces like gravity and friction that pretty much almost always oppose movement. Gravity and friction are always causing things to slow down and change their motion. They are unbalanced forces a lot of when things are moving. So if we want to actually figure out how much force that we have, we can look to the second law. And the second law says that force equals mass times acceleration. If an object starts moving, then we can calculate, if we know how heavy that object is, and we know how quickly it is speeding up or slowing down, then we can calculate the amount of force that was given to that object. Similarly, if we have one object crash into the other one, based on the mass and acceleration of that second one, we can calculate how much force the first object put into the second one. So force equals mass times acceleration. If your mass gets heavier, you're going to need more force. If you want to accelerate something more quickly, you're going to need more force. And then finally, like we were talking about today, the third law says that whenever we have these objects that interact with each other, whenever two objects collide together or hit or push on each other in some way, there is a force going one direction and there's an equal and opposite force going the opposite direction. So that's what this equal and opposite reaction means. That if a certain force is exerted on an object one way, that object will naturally push back with the same amount of force in the other way. Whether you're air pushing a rocket ship up, or birds pushing air down, or science teachers pushing on a table or a desk. If you push against something, that something will push back. Whether it's a solid like this desk, whether it's a liquid like a swimmer pushing through water, or whether it's a gas like a bird pushing through the air. Every object, all matter, when there's a force exerted against it, it'll exert a force back in the opposite direction, but the equal amount of force. So if we take all these laws together, they tell us the most basic rules for how things in the universe move. Everything in the universe has to follow these laws of motion. Again, no matter how big or how small, whether you're talking like insects and bacteria versus planets and suns, they all have to follow these basic laws of motion. We need force in order to move or speed up or slow down objects. Force is directly related to mass and acceleration. If you put in more mass, you're going to need more force. Same with acceleration. And finally, when something exerts a force against an object, that object exerts a force back. So these are true no matter what type of interaction or what type of objects that you are dealing with. All right, any final questions about our Newton's 3 laws of motion?
The unbalance is something that's still, right, ahead of you.
What was that?
Unbalanced.
So an unbalanced, hold on, where are we at? There we are. So an unbalanced force means that it's when there's an extra force that is not being counteracted by another one. So like when a book is sitting still on a table, there are forces on it, but the forces are balanced. So there's the force of gravity that pulls the book down, and the force of the table is holding the book up. But these forces are balanced. These are staying the same at all times. Now, if I came along and I like whacked the book on the side with my hand, I would be putting an unbalanced force against that book, right?
Okay.
We'll
That's what I couldn't remember.
But I'd be able to put in enough force to cause the book to move. And that's what we mean by an unbalanced force. Basically, the force of me pushing on the book would overcome the force of the book pushing back on me.
I got it. Thank you.
Mm-hmm. So when everything is balanced, so like when you're in a car that's going 60 miles an hour on the highway and you put on cruise control, so you're staying at exactly 60 miles an hour in a straight line. There's all sort of forces acting on the car, from the force of, you still have the force of gravity pulling down on the car and the road pushing up on the car. There's the force of friction on the ground and friction in the air pushing against the car to slow it down. But that's being balanced out by the force of the gas and the engine pushing that axle to move the car forward. So the speed of the car is only going to change if you put on an unbalanced force. like putting on the brake pads to slow the car down, or putting more gas and more force in the tires to get them to overcome that air resistance and that friction and go forward faster. That would be an unbalanced force. But if everything is totally balanced, then we're just going to stay at the same speed or stay completely still. All right, good question. Any other questions about our 3 laws of motion, or what any of the different parts of these laws of motion mean? All right. So I kept up with the theme of keeping pretty simple daily assignments for today and tomorrow, just to make sure that I just wanted to make sure that we're kind of getting the very basics down of these laws of motion. So today's assignment just asks you about, think up your own example of the 3rd law of motion. What's something that you maybe encounter in your daily life, or that you can think of, that is a good way of showing the 3rd law of motion, this action-reaction law? So I don't just want you to tell me what the law says. I want you to think of what's kind of like an everyday example that shows how that law works. And then for tomorrow's homework, so for your last Friday homework of term 5 and of the school year, I have a little bit trickier question. That says, when you roll a ball on the ground, it does not keep rolling forever, but eventually rolls to a stop. Why is that? What force is slowing the ball's motion? So this actually relates a little bit more back to that first law of motion that we were talking about, and some of those unbalanced forces here on Earth that can cause things to slow down and stop when they're traveling through the air or across the ground. So that's what I want you guys to do on Friday, is tell me why, if you're on Earth and you roll a ball along the ground, eventually it'll roll to a stop and it's not going to keep rolling forever and ever. So that is what is coming up for your final Thursday and Friday assignments of week 7. Does anybody have any final questions about any of the laws of motion stuff or any of your upcoming assignments?
No, sir.
No, sir.
All right, cool. Let's go back to the call now.